Yeah.
Okay.
We're delighted this week to have Elden tell us about Selmer motivic cohomology. He's
Yeah.
visiting from the University of
From yeah, this building.
Pennsylvania.
Yeah, so thanks for letting me speak here. So this will be um yeah, so I guess math falls into various activities. Sometimes it feels like war, where you have to fight through your things, and sometimes it feels like keeping your garden. So this is about keeping your garden. Yeah. Now I'll tell you about some stuff I thought about while I was in my childhood bedroom. So yeah, so let's recall the following. Let's put ourselves in the days of the Italian algebraic geometers. Yeah. So there's something called if S is a over C is a variety, right? Can somebody, maybe not Charlie, tell me the classification of surfaces by Castelnuovo? Well, like, do people know the theorem?
I can blow down a -1 curve.
Ah, so it basically, yeah. So you can build a -1 curve, and here's what it leads you to. So you can define the irregularity. So this is called the irregularity, which is dim of H1 OS, right? There's the irregularity of a surface or a variety. And then there is, again, oh, sorry, irregularity is called Q. This is like the real old school notation, okay? So don't blame me. So there's PG, which is the geometric genus, which is the dimension of H0, uh, I guess omega, yes, the omega S. And then there's also the second fluid genus. I'm going to write P2G, but I think this non-standard notation, this dim H0 omega tensor 2S. Yeah, so these are all invariants of algebraic varieties, okay? And so the theorem that is proved by the Italian school is that if S is a surface, so it's a algebraic four-dimensional complex manifold, I guess real dimension four and two dimension two complex is rational if and only if irregularity equals to the second plurigenus is zero. Okay. So you can ask, like, what happens if you drop one of these conditions, for example? Okay, like what happens if you drop one of these conditions, and like, is it like what are examples of surfaces which are not rational where you drop one of these zeroness conditions? Okay, so here's an example. Yeah, so there's the Godot surface. Okay, so yeah, so it's roughly like this. So you have you have inside P3, which has X W X Y Z. Okay. Oh wow, I got it. Um, so this is yeah, projective space with this coordinates, right? So there's an action of C5 on this thing. Good. Given by something that sends X, Y, W, X, Y, Z into yeah, I'll just look at my notes. What's this? Ah, W rho X, rho Y, rho Z. Okay. No, rho squared, sorry, rho squared, rho 4. So there's a C5 action on this P3 guy. Okay. Um, and the Godot surface, let's call it V, is the quotient of this thing. So yeah, you can check this a free action. You take P3 mod C5.
Rose.
Yeah, exactly. Where rho to the 5 is 1. Okay. So if you're a topologist, this is a way to construct something like an approximation of BC5. Okay, that's like the homotopy type, roughly speaking. And this has the feature that this is not rational. but the irregularity is zero. Q is zero. Okay. But of course, pi one is not zero.
So this thing is singular, right?
Yeah. Okay. So by this, I always mean like pick some resolution and so
Okay.
on. Yeah. I just give you a flavor of what's going on. So this go-to surface is very nice. Like various variants of this kind of construction gives you counterexamples to the integral Hodge conjecture. That's a very famous kind of story. And yeah, it's been studied kind of quite thoroughly. And it's an example of a non-rational surface where the rationality is zero. But sorry, the this irregularity is zero, but the second to origins is non-zero, so therefore it's not rational, and it's not simply connected because there's some fundamental group that pops out somewhere.
Is it important that it's five? Like that?
No, there are many other variants. Yeah. Okay, so there was a question that came up that was posed for a long time. Can we find something which is not rational, something where the irregularity is zero and the fundamental group is also zero? This is a question. And the answer is yes. And this is a theorem of Rebecca Barlow from the 80s. And she came up with something called the Barlow surface. And it's something like approximately P3 modulo D5, or like dihedral group. I mean, this is a thing of order 10. Is that okay? People write D10 or D5. What is the correct? Yeah, okay, it's the thing of order 10. So you have to twist the action by an additional like C2, and then you get something where you kind of kill off this fundamental group, which is nice. And yeah, so what does it have to do with Selmer material cohomology? You wonder? Don't worry, it will come up. And yeah, so let's call this the Barlow surface. Let's call it B.
It also came up in talk last.
Really?
This was the surface that Katsarkov et al. Found both fancy.
It's three. Ah, really? But oh yeah. Sorry. Yeah, that's you mean the talk at the AG seminar?
Yeah.
Yeah. So this is why I started with this. So so the Barlow surface, as Benji has already alluded to, like my interest in this is the following theorem due to, but so this is what it is, by the way. It's some kind of like P3 modulo D5 kind of. I mean, you have to take various kinds of resolutions and so on. But that's again.
Yeah, I take this and I take a recipe.
So no, it's a bit more complicated than that, but like it's roughly that. So you're not far from there. Okay. So there's a theorem of Bonig. Is that how you spell his name? Boning von Bottmer Katsarkov and Sosna. Yeah, so they prove the following. So if you look at perfect complexes, so the derived category of this B Barlow surface, then there's going to be 11 exceptional line bundles. So this I just generate this. Yeah, it's a surface. Yeah, B5. Yeah, so I guess yeah. So it's not really you're supposed to take like a yeah. You're supposed to take some hyper surface inside P3 and modulo by D5. That's kind of this. Yeah, it's not really that, but it's definitely a surface. Yes. Uh, yeah, yeah, right. Like it's some kind of locus of quadric, some not really quadric, quintic, I think, for this one, and then you multiply by D5. Yeah. Uh, yeah. Sorry, but anyway. Uh, yeah. So the point is that you take all these things, and there is a left orthogonal called AB, which is a phantom. So each of these on the level of K groups or whatever is going to behave like a point, basically. Okay, so K theory of this is like going to be a copy of Z. K0 of it is going to be a copy of Z. It's an exceptional line bundle. Okay. But AB is non-zero. And what they prove is that K0 of AB is zero. Okay. So this is what was talked about last week during Amal's talk. Yeah. And I want to start this Selmer motivic whatever thingy to motivate certain theorems that I know or certain uh, results in geometry. Since it's a geometry seminar, that yeah, I want to unify certain results that I know and within one framework, and this is one of them. And what we prove is that the higher k groups of this phantom is zero. So let me say that remark. This is a result due to so this is I guess Gorchinsky-Orlov is that rationally the higher k groups is zero, or the higher k groups of any phantom will be rationally zero. But it's not quite clear why the integral k groups are zero, but in this case it's actually zero. So this is I want to write this as theorem maybe one, I mean theorem A. Okay. So this is a particular story about derived categories and algebraic geometry. That's interesting, I guess. I guess at least to my viewpoints. And I want to explain why theorem A has to do with Selmer, whatever. Okay. Then I will also talk about theorem B and theorem C. There's two more. And this is like kind of going to make up the first half of the talk. Just a leisurely kind of like discussion of certain results in geometry that could be unified using the Selmer language. Any questions about this? Yes. So any phantom will have rational k groups being zero. The phantoms that Amal came up with last week, turns out that the k groups are also zero, but for easier reasons. But this one has no good reason why it's zero unless you actually prove it.
Yeah.
Okay.
Sorry, say that again. That some of them have reasons for being zero.
Yeah. So for example, if perf B has a full exceptional collection made up of like some other line bundle, then we know that the K theory is just going to split as some direct sum, right? And so there's no space for this, the higher K groups of this to be non-zero. But for this one, the BVKS phantom, like this doesn't have a full exceptional collection.
Okay, so that would show you already know that the case zero of this.
Correct.
Zero,
Yeah,
right?
I make exactly. Yeah. Correct. Yeah.
What do you know? Just false.
Well, they don't know. They don't know. Yeah. So if you know that it has full extensional collection, then that's easy. You can prove this theorem easily, but it's hard to like come up with full exceptional collections in general. Yeah.
This is a projective variety, right?
Yes.
No, negative k groups get the with thumbs up.
Yeah, exactly. It's sum and opposite. Okay. So that's you come to a geometry and physics seminar, and I'm offering you some geometry and maybe some physics if you can tell me what this has to do with physics. I mean, apparently there's some mirror symmetry, something that you can tell me. Yeah. Okay, so that's theorem A. So theorem B, yeah, I don't know why I started with this. The other theorems are much more significant. So I'll start with theorem B. So theorem B is a theorem of Reutemann and Milne. Yeah, so before I move on, because I'm gonna like kind of forget about this until I kind of explain the proof in maybe the second half of the talk. Is there any question about this story? About phantoms. So yeah, so theorem B has the following flavor. So I'm over an algebraically closed field, possibly characteristic P. So let's say X is a smooth projective a variety. Okay. So there's child zero of X, which is the group of zero cycles on X generated by points, close points of X, up to rational equivalence. And because X is smooth projective, you can talk about the degree of a variety. And you can look at those cycles of degree zero, the degree 0, 0 cycles of X. So there is a map here that people maybe that deserves to be called the Abel-Jacobi map of X. Okay. Into the Albanese variety of X I mean, this is a variety. This is like like an abelian variety. And I'm gonna look at the k bar points of those things. So this is an abelian group. Okay. And the theorem of Reutemann and Mill tells you that Aj of x is an isomorphism on torsion subgroups. So we had an entire seminar on zero cycles last time. So this is a pretty surprising and powerful theorem, I would say. Let me make some remarks about this. And also kind of make this map more explicit in some complex setting. Okay, so let me make a remark. Yeah, so when x is a curve, right, then we don't need torsion. And this is the well-known fact that pick not of x, right? So a Charles zero of a curve is going to be the Picard group, right? So degree 0, 0 cycles or degree 0 line bundles is going to be pick not of x and is representable by an abelian variety. It's representable. So Mumford proved that this is not really possible. So it's a very natural question to ask, like, are degree 0, 0 cycles for a thing which is not a curve, like a surface, is it true that you're representable? Is it the k points of an abelian variety? And Mumford proved that in general this is not possible. But the Reutemann-Milne theorem tells you this is okay on the torsion part. The torsion part is still governed by this object, and it has some remarkable consequences. So here's an example of something non-obvious that you can read off from the Reutemann-Milne theorem, right? So if I look at let's say Kc, then Charles zero of x, Charles zero x zero. So this has a map into so the Albanese, but the Albanese has another name. Let's write like this. See, it's the following. So you take h 0 of x omega 1, right? Of x dual modulo this lattice h1 h lower 1 xz. So this is like some formula for intermediate Jacobians, right? This is just another expression for the Albanese of C. Okay, and this map is given as follows. So you take a cycle here called what did I write this? Okay, so I call it Z. It's a zero cycle. It's a bunch of points. Yeah, and then I'm gonna give a linear functional on this h0. Okay, the linear functional is given by integral of gamma. Okay, blank. That's a linear functional where gamma has boundary Z. But of course, there are different choices of gamma, and you eliminate the choices by this h1, h lower 1 xz. So that's the mute, which is very explicit and very nice. But in particular, if h0 x omega 1, okay, which is like the also has the same Hodge, it's like dual to h1 xo, right? By Hodge theory. So if the irregularity is 0, then this guy is 0. Yeah. So therefore, there is no torsion 0 cycles on x. That's surprising. I think that's very hard to actually know, right? How would you know that Barlow's surface has no torsion in 0 cycles? It's like kind of imagine you have to move some cycles, and that's very hard. But the Reutemann-Milne theorem is a way that you can control torsion in 0 cycles using Hodge theoretic data. It's one of the things you should appreciate. Yeah. Any questions about this? Yeah. So that's it's a really powerful, like really awesome theorem. And that's my theorem B. Okay. So the theme that I want to emphasize in all these theorems that I'm going to state is that there is some motivic to étale kind of comparison, whatever that means. If you don't know what those words means, it's fine. But these motivic to étale maps are either in isomorphism or controllable, or isomorphism on torsion, or isomorphism on rational parts, or something, something, whatever it is. And when you can say something about this comparison, good things happen. Like you learn a lot about the motivic parts, or like the cycles, the cycle-theoretic parts. Okay. Whoa. Any questions?
So the Albanese is like the étale part.
Yeah. Yeah. I'll actually do that. Yes, I'll actually explain that. Any questions? Okay, so that's theorem B. And theorem C is something that I've been really obsessed over. That I've spoken to like people like my students or and Nick. So this Kato Saito. So the first two theorems is about things over the complex numbers. Now I want to talk about finite fields, because the whole point of Selmer is that you're supposed to take all primes and combine them together. That's what the word Selmer is most associated to it. Okay, so Kato Saito prove the following results. So you have so K is FQ now, a finite field. So you have 0 cycles inside X, right? Okay, so I'm going to construct a map to pi1 of X abelianized. Okay, so you take a cycle. So you take a cycle. You have a V inside X. Let's say close point. Okay, and what I'm going to do is so it's really a map from spec of F Q prime to X, right? It's just a close point like that. And I'm going to take what element of pi1 of X abelianized I'm going to take. I'm going to take Z lower star of the Frobenius on FQ prime. Okay. So Q prime Frobenius. Yeah. So this is called Frobenius substitution, whatever that is. Okay. And now what this does is that so you have to prove that this map factors through the equivalence relation that generates Charles 0 of X, that's like what's called reciprocity. And this map turns out to be an isomorphism after tensoring with ZP. So this is what they call like geometric class field theory. So when X is a curve, there is this it's again the Picard group comes out. Yeah, so he has the same theme as this. But let me point out that the Reutemann theorem is about the torsion part of Charles 0, right? It's about the torsion part of Charles 0, whereas the Kato-Saito theorem is about after the tensor is ZP. So it's like kind of related but different flavors. Okay. So let me make a remark. So when X the curve, people usually write maybe something like this: pick X mod P to the R is like isomorphic to pi1 X abelianized mod P to the R. It's an iso.
Is Q P to the or is Q the power?
Yeah, exactly. But the class field theory also works when P is not prime to like it's all okay. But otherwise, I mean this is harder. This is due to like Kato Saito, and also has a proof which is more readable by Koliothalan, Sansuk, Soule, when P is co-prime to Q, and by Michel Gros in his thesis when Q is the power of P. Okay.
Can I ask a question?
Yes.
Why did I need to abelianize pi1? Is it to make the equivalent?
Yeah, exactly. Yeah. Otherwise, this is an abelian group, Yeah.
Right.
Yeah. You first you complete the thing and then you prove that things are finally generated enough, which is also not obvious, so it's just as easy. It is an ISO after by completion as well. Yes. I like this statement more though, somewhat, you know, because it also captures the fact that this tau zero is in a non-obvious way a finitely generated abelian group in this case. Okay. Okay, so that's the theorem. And theorem C is related to theorem C prime. So I'll tell you what C prime is. Yeah.
Right?
Yeah. Yeah.
Seriously.
Yes.
Opens.
Yes.
So the
Isomorphism on torsions
night.
on finite fields.
Yes.
Yeah, actually I don't know this. Do you know?
Conjecturally.
Conjecturally.
Yes.
Yeah. So
Range.
so there's a map from Charles 0 x 0 cycles into the Albanese as well of x in over finite fields. Like degree 0 0 cycles on x into Albanese. So there's a Whiteman style question you can ask about this. Yeah, I mean,
Oh, sorry, the point.
yeah, points. Yeah, exactly. Yeah, yeah. Yeah, some conjecture.
If it's where it's not this included for that Charles zero of x is declared in instance of the first points that they have to be right.
Yeah, yeah, yeah. Right, right. No, but it doesn't say. But even in Whiteman, it says nothing about the divisible parts of Charles 0.
The torsion
It's the torsion part, only the torsion part. Whiteman is algebraically closed fields. Yes.
Yes.
Finite fields. Yes.
Well, if we chose.
Uh, uh, Up to P completion. Yeah, Charles 0 of x is the pro-finite part is like finitely generated. Does that make sense? Uh, it is finite. Yeah, it's a finite group. Yes, yes, that's right. Okay, yeah, it is a finite group. Yes. No, wait, no, no, there is a wait, no, no, there's a z hat somewhere. No, there's at least one z hat.
Same. Zero, so you can do it.
Yes, exactly. Yeah, yeah, remove it. Yeah, if you put degree 0, then it's going to be a finite. Yeah. Yes.
Keep backwards.
Yes.
But the shall best they teach the
Uh-huh.
best.
That's correct. Yes. Albanese of the FB bar. But yes. Yeah. Any other questions about this? I'm going to turn it into a C prime and tell you that this is the same phenomenon. Okay. So C prime is, these are all very old theorems. I guess I'm going in reverse chronological order. So C prime, what?
Right. C.
C is, this is an isooptic tensor with ZP. Yeah. Yeah.
It's a computer thing.
No, 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 this will be finally generated after a tensor is ZP. It's not, the what? It is. No, this will be over. No, over finite fields? I claim it's not. Yeah.
That's not.
Yeah.
That's right. Okay. So take X to be spec up too. Let me see how.
Uh, yeah. How do I write the correct statement? I mean, yeah. So for mod P to R for every P and R, uh, this is going to be a finally generated group. That's what I'm saying.
Yeah. Yeah. Then we this prediction. So let's take for X just a spec at P.
Yes.
Then
It's going to be Z to Z hat.
agree.
Yeah. Yeah. Just, okay, but Yeah, maybe I should say okay, sorry. Yeah, maybe I think what Michael wants me to say is like replace this with this inverse limit on the left. Yeah, okay. Yeah.
Maybe you're doing this in such a
No, no, I don't want to do that. But
so
let's take the inverse limit on the left. Let's do that. On the right.
you could say this is a profiling equation.
Sure. Yeah, sure. Profinite completions. Yeah. Yeah. No, no, but yeah, you're right. There's some z hat on the right.
The way I'm supposed to understand this is like pi one of x, the abelianization, like a priori, there could have been like all kinds of stuff
Yes.
there. But
Yes.
like it turns out it's all just loops.
Yes. Yeah, exactly. Mhm. Yeah, as you say, so like classical theory attempts to understand the thing on the right up to abelianization in terms of something more geometric, something on the left, right? So like the thing you're interested in is this, and that's the thing that is somewhat accessible, or at least that's the propaganda of old school classical theory, right?
So in old school classical theory,
Yeah.
is a statement that according to Corbin uses time to become quantum machine or instance. By just
Yes.
or improvements or to quantum machine or system. No, but there's a
Yes. Yeah. Representations of pi one versus yes. Yeah. I'm sure there are, but I don't know how to formulate it at the moment. But there are. You take Hom into something, right? You take functors into something or Hom into something, and you get representations of pi one is equivalent to some kind of data on zero cycles, duals of zero cycles.
Yeah, but this statement, geometric right classical theory does not well make sense over any not necessarily right.
True.
See that there is geometric formulations this type of statement which makes sense.
Oh. Well, this is what we're working on. This is what Nick and I are working on. Yes. Okay, but this is the cohomological Kato-Saito. Yeah. Okay, yeah. So again, yeah, this is kind of beautiful. But it's a C prime. So let me write C prime here. And yeah, so theorem C prime, maybe I want to stick with big F to be FQ of a curve. So C is a curve now, smooth projective. Or, well, I guess if I write like this is okay. So there's something related to this. These two things are actually combines into one statement. You can take the Brouwer group of F and map this into direct sum. H1 of let's say F completed at V. So V is a place or a dimension 0 point of C. Q mod Z. The semantic Q mod Z. Right. So this is the and this is like what Hasse, like Brouwer, Hasse and Noether. This is the so-called local to global principle, which tells you how to compute the Brouwer group of F in terms of these local contributions.
Okay, what is the C sub zero?
Just like all the places of this function field or the points of of the curve. Okay, all the valuations.
Close points.
Yes, close points. Yeah. So dimension 0 points in this case. Yeah. Okay. So codimensions. Yeah, whatever. Close points. Yeah. So there's another theorem. This is like within the whole classical theory package, I guess, and you would encounter this theorem and maybe the curve case of this theorem in like a undergrad class in classical theory, if there's one that I teach. So yes. Okay. Yeah. So any questions so far? So we talk about phantoms. They're like, oh, phantoms. Yeah.
So T is for surfaces. Yes, the variance of curves.
Yes. No. C is for any variety. Yes. It's only for curves. You can ask if there are analogs of this in higher dimension. There are. That's one of the things I want to explain. Yeah. But yeah, so these are like kind of geometric phenomenon. I mean, it's a geometry seminar. Yeah.
That's what theorem C takes. Curve. What's the relation to C prime?
Yeah, I'll tell you in a moment. Yeah. So basically, okay, so just to maybe jump ahead, okay, so there's some motivic homology, there's some symptomic homology, there's a co-fiber term, right? And you're writing some Gersten complex to the co-fiber term. It's kind of the point. Let's, I mean, this looks like a Gersten complex. There's a field, there's like points. Yeah. Okay.
So in
Yeah.
particular, it should not a priori be obvious, like these are
No,
related.
it's not obvious. Yeah. But yeah, so these are three kind of geometric games. One in, I mean, the first one is purely over C. I mean, I guess people can talk about this Barlow stuff in characteristic P, but I've tried to look for papers. I cannot find anything. And then theorem B is Reutemann, which is and Milne. So Milne does it in characteristic P, and yeah, and it's like something over something that mixes both positive and mixed characteristic. And theorem C is something over finite fields. Okay, right. So yeah, I wanna explain how everything kind of fits into a single picture, I guess. But I'm gonna I've made like two hot turns. I'm gonna make one more. Okay. But any questions before I proceed? Any other questions? No. Comments, concerns? Okay. So the way that you should think about all this phenomenon, or rather, the thing I want to convince you of is that Salmer motivic homology or Salmer K theory due to Dustin Thousand. It's like a good way to unify all these ideas. Okay. So I'll remind you what this thing is first, and maybe I'll tell you about how to think about Salmer K theory, and then we can take a break. Okay. So here's the definition. And this is due to Dustin and it's starting in his thesis. Okay. So C is a stable infinity category. I guess nowadays it's fashionable to say dualizable, but whatever. Anything you can take K theory of. Then by definition, the Salmo K theory of C, K cell of C, is the following pullback. Okay. So you have something called topological cyclic homology. So I'll tell you what these things are, the identity of these things in a moment, but just for people who know, so there's this TC of C. So there's a map here to the KU localization of TC of C. And then there's the trace map in KU localize C. So you take this pullback square. Okay. So yeah, what the hell is it? Like I just told you some concrete geometric stuff, and okay, you should rightly be pissed about like what am I doing? Okay. Um so yeah, so here's how things look like. Okay, yes. So the first thing that you should ask me about is like what is LKU? Okay. I don't know, I don't care, but the thing you should know about LKU is that if I take LKU of anything, okay, if I rationalize this, then it's equivalent to the rationalization of E. Okay? Doesn't change the rational values. It's just whatever it is, doesn't change the rational values. Okay? Okay. Any questions, by the way? Like, except like, what is a spectrum? Do not ask me that. Okay, these are cohomology theories, whatever. Okay, so because of this, what I learned is that TC of C rationalized mapping to LKU TC of C rationalized, it's an equivalence. So LKU K of C, which has a map from K of C, is a rational equivalence. Okay. And therefore, because equivalences are stable on the pullbacks, Salmon K theory of C, tensor Q, is equivalent to K theory of C. So I do not change the rational values of of K theory of C. Okay, so whatever it is, like K theory contains some geometric thingy, and yeah. So rationally, I do not change this. Okay, that's the first thing you should. This is a rational structure. Okay. So that's good, right? Or like maybe that's what you want. Uh, so another good remark. Okay, it's like P periodic. C. So this just means that 1 over P is in C, so C is P X invertibly on C. Okay. Then what? Then if I take THH of C, so this TC object is obtained from something called THH. This is also P periodic. So Px invertibly on this because THH is linear over C. Yeah. And therefore, if I take TC of C, this will still be P periodic. So if I P complete something which is P periodic, this is going to die. Okay. So this is a map to LCDH. Yes, sorry, LCDH, LKU TC of C. Okay. P completed. And this is also going to be 0 because I've KU localized something which is 0. So therefore, yeah, so this is an equivalence in particular because 0 is equals to 0. So then if I take KU localized K theory of C, so I take this left corner, I P complete this. And if you, okay, so I'm going to start writing this as LK1 of K of C, which just out of habit, feel free to ignore this if you, or like do not ignore it, substitute in your head. But yeah, the correct thing is K1 localized. And so this will be an equivalence as well. So this is K of C, P completed, right? Yeah. So when you P completes something where P is invertible inside, then the summer K theory of C is going to be this K1 local K theory of C, which is a familiar looking object to some people, namely Robert Thomason. Yeah, so that's so there's this contribution when the input is 1 over P, C is P periodic.
Should I interpret, because you didn't write a P as block, should I interpret that to mean non-linear?
Yeah, no, there's a P. So anytime I do this K1 local, there's some implicit P. This is like the worst habit of every topologist. So, yeah. Okay. Any questions about this? So that's rational structure. That's P periodic. So what happens when C is P complete or P Henselian? Yeah. So suppose that so I'm gonna let R be a okay connective E1 ring where pi 0 of R. This is very awkward, but I apologize. I'll tell you examples. Commutative and P Henselian. Complete. Okay, so things like ZP, okay, like things like ZP, finite ZP algebras, things which are, yeah. So E1 just means like associative, right? And connective, yeah, you can ignore what it means, but it's connective. And pi 0 must be commutative, and P and but pi 0 bar is a P Henselian ring or P complete ring. Then what do you get? Okay, then yeah, then if I take Sumner K theory of this R, so by taking Sumner K theory of R means I take perfect complexes on R, like R modules. Okay. But P complete this will be an equivalence with the TC part, TC R, P completed. Okay, so let me explain quickly why Sumner K theory of K LKU LK1 of R, P completed LK1 of TCR be completed. So to prove this is an equivalence, I just have to prove that this is an equivalence. So I'm looking at LK1 of K theory of R mod P completed, and LK1 of TC of R mod P completed. So there's some implicit pi zero there because like we connected P1. Okay, I'll write the pi zero because why not? Right. So I claim that this is 0 because if I take K theory of FP and P completed, then this is ZP in degree 0. And whatever I do, if I K1 localize, I'm going to be 0. This K1 localizes to 0 because it's just a single discrete ring. And so since this is a module over this, that's going to be 0. And that's a ring map. So 0 gets sent to 0. So that's 0. So that's an equivalence. So this is an equivalence. So this is a pullback because of Dundas, William McCarthy, and Carls and Matthew Morrow. Yeah, sorry, that's a bit fast, but if you are not familiar with trace methods, you can feel free to ignore it. But just take away that on the P part is going to be this thing called topological cyclic homology, which is built on PHH. If you know some trace methods, then this is like the proof that this 0 equals to 0, and therefore this is an equivalence, and therefore the top thing is an equivalent.
So sorry, just what was that was a little clear. The fact that the left-hand term, the bottom left is 0.
Yeah.
So you have the calculation of K theory of FP.
So this is a K. So K1 localizes, I get 0.
Yeah.
So this is a module. This is a module over the 0 ring, which is 0 exercise.
What are we using? Possible mapping narrow form?
P Henzelian. And not penile-potent.
Oh, I see.
That's really not okay. Yeah.
So it's why the second rule is
Yes.
Are you saying that A1 localization of CP was a very complex, but
Yes.
is always
K1 localization of any spectrum which is bounded above is 0. Because you're going to periodize something and you're going to hit 0 somewhere and it just dies. K1 localization is inverting some element, right? So if you're bounded above, then you're going to hit something where it's 0 and you're going to spread the 0 everywhere. Okay. So all right. So so if these are not very familiar objects to you, then that's good because I want to relate this to familiar objects by giving filtrations on the Summer K theory. And yeah, so that's what I will do in the next hour.
So in theory, you told us everything about the Selmer K theory. I mean, you told us what it does if C has a 1 over P in it.
Yes.
You told us what happens if C is P complete.
Yes. Yeah, yes. Okay, so maybe I'll end off with one last thing. Yeah, so if I so maybe here's a one last thing. Yes, so final remark, and this is due to Bud, Klaus, and Matthew. Yeah, so soon there'll be Kim there. There will be Hyung Sub's thesis. I'm gonna give a different perspective on his thesis, but yeah, just to make Michael happy. So there is the following pullback square that you can put K cell of R. Let's say R is commutative. You take K cell, I'm going to P complete outside, K cell of R 1 over P. I'm going to P complete outside, and then I'm going to K cell of R, P completed, and then K cell of R, P completed 1 over P outside, 1 over P inside, and P complete outside. Okay. So this is just your usual fracture square inside, and you apply Summer K theory to it. Okay, so like you can take R, you can break it down into the P completion, the P inversion, and the rigid term, as people like to call it. So this is a pullback, okay, by general reasons. This is true for any localizing invariant. And this pullback square is the same thing as the defining pullback square. LK1 K theory of R, LK1 P completed, LK1 TC of R, P completed, and then TC of R, P completed. Yeah, so the content being that I can re-express K1 local TC P completed as some kind of K theoretic object.
Right, we'll now have a 5-minute break. People would like to get some tea downstairs, and then reconvene for the second half. Um, no, I know
It's too hot. Okay.
You mind?
Yes, serious.
Serious stuff. Okay.
Feels like it was just here. All right. We
Enough about that finish. We can continue with part 2 of the talk when we are
Okay.
going to learn how Selmer K theory relates to the first
Anything.
part of the talk.
Yes. So, yeah, welcome back. Yeah, so I'll start by stating this how the theorem goes. Yeah, so I think if Muddy remembers how he was in my office and I was telling him like, we can glue all these 9 things together, but you can do it in one shot. This is kind of the magic. So yeah, so let's say X is a quasi-compact, quasi-separated derived scheme. Whatever, some very general thing, then there exists a filtration, called the motivic filtration on Selmer K theory of X. So this is a multiplicative exhaustive, but not necessarily complete, always. Filtration. Okay. Of course, functorial, whatever, all the nice things. Okay. Such that okay, the such that such that it refines this L this the pullback sphere, the defining pullback sphere, K cell TC of X of L KU of K of X LKU of TC of X. Okay. So let me be more precise about this. Okay. So yeah, so I want to make a remark before I really kind of elaborate on what the terms are. So let me make a remark that the if I P complete this left corner, this is the filtration by mark 1 filtration by Thomason. Okay, who's graded pieces, and this is how it's related to the things that we've talked about. The étale homology of the generic fiber. Okay. So there's a filtration on this left-hand side given by Thomason, whose graded pieces is étale homology with appropriate shifts. So maybe I take Ger star to star. And really, it only depends on the generic fiber. Okay. But on the right, there is some filtration that's constructed by Batmore-Schulze. And I'm K1 localizing the Butt-Schulze filtration. But there's something wrong with doing this, okay? If I K1 localize on the nose, then this is 0. Because this is a ZP module, and if I just K1 localize ZP modules, I get 0. It's terrible. I shouldn't do this. So there's a problem. So there's a problem with like gluing the Thomason filtration along the BMS filtration, and this was overcame by Hyungsip in his thesis. So he proves that this thing is filtered by étale cohomology of this rigid generic fiber. So 1/PP completed.
And what's the issue?
Yeah. So the filtration here are of very different nature, right? So one comes from this Thomason filtration is the observation that this thing has étale descent. And this thing is obtained by first restricting to like quasi-regular semi-perfectoid, right kind extending, and all the BMS construction. So a priori, like the filtration on the left and on the right are different, are like of a different nature. But Hyungsip overcame this by proving a filtered analog or filtered refinement of the Blood-Clausen-Matthews theorem.
It's the same filtration. You just proved that at 0.
Yes, exactly. Yeah. Okay, so this is what happens on the P part. So on the P part, on the yes,
On the
yes, this is
those are similar to graded pieces. The difference there is that you decomplete.
yes, the P complete inside. So there's some kind of rigid analytic fiber, like so on an open on an affine patch, you take R, you P complete first, and then you P invert. Okay.
All right, so I'm just trying to understand.
So the thing that you're saying is the reason that something non-obvious is happening is the
Yeah.
graded pieces are not taking local.
Yes.
So you can't take
No.
like a regular filtration on K1 local.
Absolutely not. Exactly.
You have to do something else.
Yes.
On a K1 local thing, the filtration, the associated graded is no longer K1.
Absolutely.
Can you say that one more time?
So if I were to just K1, okay, so you have a map between Q of X and TC of X, okay? So there's a map between the filtrations here and the filtrations there, okay? Without Q1 localization, let's say. Okay, no, maybe not.
Just
Sorry.
K1 localize those filtrations.
Yeah, I get 0. Yeah.
So whatever map is
Yeah.
not so the statement is
Yeah.
that the map is not the
Yeah.
K1 localization
No.
of the obvious map between filtered objects.
No.
That like the map can only be constructed after you K1 localize their features.
Absolutely. You shouldn't be K1 localizing graded pieces.
You're not K1 local, you're K1 localizing the filtration.
No, same thing. Yeah. 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 So that's what Hyungsip does. So what Hyungsip does is basically show that you can recover the Thomason filtration by the BMS procedure. Just after content, just this is nice. Okay, so that's the first remark. So the second remark, yeah, so étale cohomology pops out, right? So if you yeah, so like there's this, I've been alluding to pi 1 abilinize being some étale cohomology. I've been alluding to the Albanese being some kind of like étale cohomology, and this corner is somehow the étale cohomology when P is invertible. Okay, when P is not invertible, you're supposed to look at this TC of X. That's you make a second remark. So remark 2. Okay, if I just P complete everywhere, so but Lurie. So what they do is they construct the following version of symptomic cohomology, which takes in a scheme and not a P complete scheme. So BMS, the input must be a ring, which is P complete. Okay, like otherwise this quasi-regular yada yada doesn't make sense. So they decomplete this. So let's call this the Butler symptomic cohomology. So you have X, and then you have ZP star. This is coming from the Butt-Schulze filtration. So the world of prismatic cohomology that you might be familiar with at the end of the semester, thanks to Vadik, lies here. Okay, can this be complete? And there is R gamma et al. Of R 1 over P, yeah, mu ZP star. of R gamma étale are P completed 1 over P ZP star. But Louis proof, or rather they constructed the integral prismatic homology or prismatic homology, symptomic homology that takes in a scheme via taking this kind of pullback. The content being the production of this symptomic to étale comparison map. Okay, so they construct this, and what this theorem does is to refine this on the filtered level. I mean, on the graded pieces, you know what's going on, and then you make some filtered level. This is what happens on the P-complete piece. Yeah. So if you are at this juncture, Joseph just forgot to write this a corollary, but he could have done it. Yeah. Once you know how to make the bottom map filtered, which is what he does, you just attach this filtration on TC on the right, and you're okay. Joseph. Yeah. So on graded pieces, when you P complete, you get this pullback square. Okay. Yeah. But of course, you have to attach the filtration, so you have to do some work, right? Okay. So then there's rational. Yeah. So the relevance of this is that this thing on the right, on the top right corner, is the appropriate thing you're supposed to put in all the Reutemann story and all the. I mean, the reason why Milne's name is there is because this homology theory on the right is the correct thing when you're at the characteristic P and you're looking at P torsion. Okay, like even in Kato Saito and Milne, you need this thing on the right, where R is a characteristic P scheme, so you don't need to P complete, it's really characteristic P. Okay. So this is the correct thing to do with étale homology at the bat prime. This is the étale homology that you're used to, and this is like the correct version of étale homology at the bat prime.
Related to the LP.
Yeah, I'll do that in a moment. Yeah. Yeah, so I'll do all the manipulation and then I'll only tell you the proof at the end. Like I'll do the Albanese things first. Okay. But before that, let me make one last remark. Is that rationally, so on graded pieces, yeah, so modes 2J star 2 star is the graded pieces of Selmer K theory rationalized, and this is like rational motivic homology, which is already known by Adams operations, by Adams operations. So you don't need anything beyond AD's mathematics. Once you know how to define Adams operations on an arbitrary ring, you can define rational motivic homology. And what this does is that on rational pieces, it's supposed to be the same thing as K theory because K cell rational is rational K theory. So you recover the Adams operation. You recover the eigen spectra, eigen complexes, eigen things. Yeah, that you might be used to. And yeah, so you can ask Ismail all about rational K theory. It's what you think it is. It's the same. Up to with indexing. All right. So I want to relay this to yeah. So the story. Yeah.
The fact that there's cell that appears
Yes.
right hand side is irrelevant, right? If it's
Yeah, because cell is K. Yeah.
Ger.
Yeah, like this. So I want to retell the stories A to C. So there is Selmer K theory. Okay, sorry, there's usual K theory of X. There is Selmer K theory of X. And I'm gonna name the cone as Matthew and I did. We call it Kato K theory. This has been maybe a Toronto only name. Okay, so the graded pieces here is motivic homology in the sense of my stuff with Matthew and Tasbuis. So that's graded pieces. This is like full-on motivic homology of any derived scheme. And when you are classical, when X is like a smooth variety over a field, then it's going to be Chow groups and all the usual algebraic cycles thing that you like. So this has a map to Z star cell. Okay. And So of course the cone is called Z star Kato. And so in this papers with Tom and Matthew and so on, we have like the mod P version of Z star Kato, and what I wanted to do was to have a like a full on integral theory. So you just stick in the Q actually, but you have to like justify why you can stick in zero. I mean, you're supposed to stick in zero. Rationally, they're the same, right? I just wanted to, yeah. So this is the co-fiber of this motivic to Selmer map, and it's rationally zero. Yeah. Okay.
So because you there's no thing up here on the left.
This thing.
The
Oh, P completion is Z star cell P completes to Z star BL. Yeah.
So C star cell is the definition of the piece associated gradient pieces.
Yes, that's right.
Operation.
Yes, exactly. Yes. So Ver star is this row. Okay. All right. So let me talk about what Benji requested. Okay. So Benji wanted to see how the Albanese comes up. Yeah. So let me tell about this Reutemann story. Maybe I've told some people here, and it's like kind of boring. But okay, let me stick this. So let me produce the Albanese out of étale cohomology, right? So we have x over k equals to k bar. The smooth projective is only needed basically at the very end. Okay, so we have 0 to pick naught of x mapping to pick of x mapping to the Narancivari of x. Yeah, so this is the degree 0 line bundle. That's the leftover Narancivari thing, lattice. So I'm gonna hom of mu m inside in the category of abelian sheaves over x. So all abelian sheaves. I'm gonna get 0 to hom mu m pick naught x to hom mu m pick of x mapping to hom mu m of the Narancivari of x. Okay, so now this is actually 0 because the xth one into an abelian variety is 0. It's like it behaves like a divisible group in the world of abelian sheaves. And the one thing you have to know about Albanese is that it's dual to pick. So by duality, this becomes hom from the Albanese of x and just the m torsion part into z mod m. Okay. Yeah. So far, so good. Are you okay with this, Benji? Yeah. Okay, then I dualize again. I'm gonna hom into z mod m again. Yeah, so I'm gonna punch dragon dual or hom into z mod m. So I'm gonna get 0. So hom of mu m Narancivari x dual, so like this, the z mod m dual is maps into hom of mu m into pick x dual, and I'm gonna map into the Albanese of x without the dual because this is the thing that comes on the dual, the n torsion. Okay. So can somebody spot the étale cohomology? Yes, exactly. So this is isomorphic. I mean, pick is like H1. I do some kind of dual, and the end process is étale cohomology of x of z mod m coefficients. Okay. So Albanese is not on the nose H1 étale x mod m, not on the nose. Okay, are you okay with this? Yeah. So pick becomes H1 some mu m, and then the mu m's and the mu m's kind of dualizes to H1 x z mod m. You can work it out. So, but if I take the co-limits as n goes to infinity, then with this form of mu m, neuron severity x dual. So this is the co-limit of the system, which is the dual of the inverse limit system. Okay, and you can show that because there's neuron severity x is a finite group scheme. This is going to be 0. So what we conclude is that h1 of x, sorry, take the limit. Yes, limit. Yes, take the limit of the dual, which is co-limit of the. You take the co-limit first, and then the dualization. So you get the étale homology of the middle part is isomorphic to the Elb X torus, the torsion part of Albanese. All right. So what does this have to do with motivic whatever? Yeah. So the key to Reutemann is the following. Suppose you want to study. So I'm just going to put a surface. 4 is just 2D, but yeah. So the proof reduces all the way down to a surface. Okay. So there's motivic cohomology, which is the fourth cohomology of the weight to object that I just erased. And I look at the M torsion subgroup of this H42. So the one thing you have to know that because X is a surface, this is going to be Chow 0 of X M torsion, right? So this maps to the via the Abel-Jacobi map into Albanese of X, okay, M torsion. Okay, so the beauty or like the power of motivic cohomology boils down to the following very humble fact that you can put something naturally boundary into 4. Okay, so I'm going to write like this. So H3 mode of X Z mod M 2. Use the boundary map. That's subjective. If I just gave you this Chow 0 of X, you know nothing about the thing that comes from the left. If you do not know it comes from cohomology, but this is just the Bockstein sequence in cohomology. Okay, so this thing is very good because this is the spot where the motivic to étale is an equivalence. Okay, so H3 mode of X is étale Z mod M2. Yeah, so when I'm not telling, I haven't told you when you can predict motivic to étale being an equivalence. Okay, but when you're a surface over an algebraically closed field, this is the number 2 that's important. This H3 mode and H3 at is equal. That's the theorem.
Why is that? What was the number 2 important?
Yeah. So this you can cite Suslin. So Suslin says when you're over algebraically closed fields, okay, and your D, your weight, is at the dimension and above, then this becomes iso. Okay.
So the 3 is around.
3 is irrelevant for this. Yes. So that's over algebraically closed field. That uses algebraically closed field. So for example, Wygotsky's Fields Medal winning work is when this number is higher than this number. Then that's always true without conditions. So this violates it, but like there's a place where when the weight is too high, namely at the dimension and above, then it becomes iso again. Okay. Yeah. Okay. So now, but okay. So H3 étale is isomorphic to like there's really no direction here. I'm gonna use Poincare duality to H1 étale XZ. There's a dual, right? I'm gonna get confused over the dual, but sorry, dual here.
Where did the M go?
Yeah.
Where did the M go?
Zimon, I'm sorry. Yeah. So I was too rushed. Yeah. Yeah, sorry. Yeah, there should be a dual. I dropped a dual here. Yeah, there's a dual there.
Simple.
What? Uh, no. So you take the limit. Yeah. Sorry. You're right. Co-limit, and then there's a dual. Yes. Okay. Good. Yeah. So there's a map like that, and so kind of this commutative diagram plus really trust me, like basic homological algebra gives you Whiteman's theorem. So the key point is this isomorphism. Okay. And the fact that you can reproduce the Albanese as close as possible to étale homology. You get Whiteman's theorem that way. So this, if you remember this, you remember the proof. Okay.
Wait, so what did all this give me? All this gave me a map from
Yeah.
the étale to the Albany.
Yeah. So you just this kind of comparison. Then you still have to study the kernel of both sides, but you end up proving that this thing is an isomorphism by proving that this thing is an isomorphism. Here's the thing. Yeah.
What's the kernel of delta?
Is H3xz modulo H3xz times n. Yeah. So yeah, exactly. Okay, but the key point is this diagram, really. That you can reformulate this Albanese object in terms of étale homology, like subjecting onto by some étale homology. Yeah. So okay. Yeah. So like without knowing this object, you wouldn't have known how to construct something which is subjecting onto H4 that maps into Albanese. Okay. So that's the story of Whiteman's theorem. Any other questions? That's the key diagram in proving Whiteman's theorem. Okay, so that's like story B, I guess. Right. So story C, C prime, which is about this this like Kato-Saito higher class field theory thing. Okay. So the point, so for this thing, you have to do the following. So you look at so I'm over a finite field now. Smooth projective. Yes. So the key point, or like one of the key observations, is that pi 1 of x abelianized, okay, is dual, I guess, mod p to the r is going to be h, is going to be, I'm gonna mess this up, I think. So let me, so, okay, I'm gonna get the numbers wrong because I forgot what it is, but pi 1 of x abelianized, just as in topology, is h1 like étale or symptomic or whatever with z mod p to the r. Okay, it's like it has the same like this formula of like abelianization is the h lower 1, but there's going to be some dual to h2d plus 1 symptomic or étale. So the numbers I'm fudging a bit, but z mod p to the r d. Yeah, I think this is correct. So this 1 has to do with the fact that you're over a finite field, so you have cohomological dimension 1. You have to like add on this 1 somewhere. Okay. Dual. Yes. No, dual, like here. Yes.
What goes in the H1 of what?
X. So the map, the Frobenius substitution map to this pi 1 x abelianized can also be thought of as a comparison between motivic to étale homology. Okay. It's like it's motivic to symptomic or étale homology. It's within the same realm. And the way that you think about Kato-Saito is the following. So this Kato Saito. So you have motivic homology of weight D. So you get like the zero cycle. So D is a dimension. Let's write on X like this. So D is dim X. And then you look at, so this is mode. So Z mod P to the R D, and then this is sin or étale. Like by this, I mean, yeah, so let me just write like this. So this has two values, okay? If 1 over P, or if Q and P are coprime, this is just usual étale homology. Yeah. Okay. So it has this Salmor K theory kind of flavor. When P is invertible, it's just étale homology. Otherwise, it's this, yeah, I'm going to write symptomic homology, which is the correct version when P divides Q. Okay. And so there's the co-fiber, which is Kato homology, Cp to the Rd Kato of X. Okay. And the Kato-Saito theorem tells you that the motivic to symptomic homology, when X is smooth projective, is an equivalence after P completion at the top degree. But what is conjectured is that it should be 0 for D at the dimension of X when X is smooth projective. Yeah. So if Q and P are co-prime, then this is there's a theorem of Moritz, Kurtz, and Shuji Saito. But otherwise, this is still open.
So this is the conjecture that this is 0 when this is smooth projective.
Yes. So Kato Saito proves that this is an isomorphism at the very top degree, recovering child groups versus pi 1 abelianized. But when X is smooth projective, but in fact, this whole complex should just die at the weight D when X is smooth projective.
Nice works.
Yes. No, every degree at the weight D. Yes. Yeah, every degree at the weight. So when Q and P is co-prime, this is known.
Q is the size of the
Q is the size.
Q, what is Q?
Q is P to the R. Q is P to the N.
Yeah, it's that.
Oh yeah. Well, okay. Yeah, I don't know. Okay, 1 over P is an FQ, and then else. How about that? Okay. Is that okay?
No.
Really? Why not?
Yes.
It's a the Q is not like Q is the other.
Yeah.
No, Q is some power.
Yeah.
That is not fine.
Probably is all.
Yeah.
Okay, yeah. L to the N. I don't know. Yes. Yeah. Okay. So, sorry. Yeah. No, it's not. Sorry, it's not 0, but it's like concentrated. Sorry, in degrees, only D plus 1. It's 2D plus 1. There's like one last place where it's like it's not an iso, but the conjecture is that it's an iso up to degree 2D. And degree 2D is this chow 0 to pi 1 thing, and 2D plus 1 is like an extra bit floating around that has to do with FQ being Galois homological dimension 1. Yeah. So that's yet another instance of like the motivic to symptomic homology being a comparison, like another instance of this comparison thing. Any questions? So I want to talk about A.
So,
Yeah. Yes.
Sorry, how did Selmer K theory relate to all of this?
Yeah. So this is the graded pieces on Selmer K theory. Yes. So this is the graded pieces of K theory, the graded pieces of Selmer K theory at these various primes.
Point is, I'm assuming the graded pieces of Selmer K theory are something about étale.
Correct. Yes, étale symptomic homology. Yes, depending on like whether a P is invertible, P is not, and it's just a uniform name for this object, no matter who you are, no matter what input you put in. Yeah, and then rationally they're the same.
It's also natural that like they still has all cells.
Correct.
So they would take the whole.
Yes.
So like whatever étale K theory should mean, I
Yes.
should have defined it as self-replicative the way.
Absolutely. Yes, there's a good essay. It's a good étale K theory, and I'll at the very last, I don't know, 10 minutes, tell you how it's good in a very precise way. Okay. So I'll finish off quickly with story A. So with Nick, other Nick, we define the following invariants, which is cute. So we say that so LQ stands for Lichtenbaum-Quillen, P stands for prime of a category C is less than or equals to D if I take K of C, P completed, mapping to L K1 KC has co-fiber in degrees at most D minus 2.
Use keyboard.
So C has G Lichtenbaum-Quillen dimension less than D. If I take the cone and it's at most D minus 2. Okay. That's an invariant. And notice that this invariant can be stated on the level of a category. It doesn't nothing to do with schemes. Yeah. Some category dimension of the category. And but on schemes you can get something. So
Should I think of this fiber up there?
what?
Whole fiber has that.
Has homotopy groups up to D minus 2. So there is going to be isomorphism when you're high enough, which is exactly what the Lichtenbaum-Quillen conjecture was. Yeah.
Are you saying you want me to think about this as something assigned to a category?
It's a theorem. Yes. Okay. This is Rose-Vygotsky. Is that if C is perfect, and 1 over P is in OX, and X is over. I'm just going to write something simple. Okay, so R equals to K bar over algebraically closed. Then the Lichtenbaum-Quillen dimension at P of C is at most the dimension of X. Yeah, X is smooth. It's smooth, finite, smooth. So it tells you the exact place when K theory becomes K1 local K theory. Okay, and I'm over the complex numbers. Let's say when K is C, then K1 local K theory of a variety is nothing but topological K theory of a variety P completed. So it's telling you when topology starts taking over. In particular, like the groups are too periodic beyond, let's say, degree D minus 1, when you are equivalent amount dimension less than or equals to D. So the magic of this definition is that sometimes this dimension is lower. Okay. I give you a stupid example and a smart example. The stupid example is that dim PLQ of X times projective space is always just dimension PLQ of X. Okay, the projective space is only going to contribute K theory of the field. Not going to do anything more. So which is less than the dimension of, well, less than or equals to the dimension of x times PR, which is x times r. Yeah, and in fact, yeah, this makes sense. Okay, so in fact, the theorem, I'm going to just briefly say that this is a birational invariant. And this Barlow theorem, this Barlow surface thing, the key point is that the Lichtenbaum Coulomb dimension of a Barlow surface is always zero. So this is a surface, but it has zero Lichtenbaum Coulomb dimension, and all the groups are periodic. It's kind of funky. And the way you do this is to analyze this difference between motivic and étale cohomology of the Barlow surface, which you can do. It's the surface, like you can name everything. Okay. And so the phantom is really just the zero phantom spreads everywhere, all the phantoms.
So it says that collective cohomology dies,
Yes.
and then what is happening to the phantom?
So the phantom is K0 being zero. So then K2 is zero, then K4 is zero, K is zero. And then you just have to check some K1 thing. You can just do that by hand. Okay. Yeah, so that's the meaning of the theorem. Okay. All right, so
this theorem implies the K theory of the phantom is two periodic.
yes, exactly. Yes. The K theory of phantom is two periodic. Thank you. That's exactly the right thing to say. And yeah, but it really uses so in fact for any variety with any surface, sorry, not variety, with irregularity 0, the Lichtenbaum Coulomb dimension is just always 0. That's what implies this theorem. So it tells you that this Kato cohomology over C contains some birational information. It's not just purely fun. No, it just contains some serious information. Okay. All right. So last 8 minutes, I want to tell you like how to construct this thing. Okay. So maybe construction of this filtration. And yes. So I'm going to use the person who's not here. So Anala Hoiwa Iwasa. Okay, so these guys construct this category of non-A1 invariant motivic spectra. Okay, so roughly speaking, to any scheme X, any derived scheme, I can construct for you like this thing called motivic spectra over X. So if X has the structure map to spec Z, then there's a pullback. MSK.
It's KZ.
What?
It's KZ.
Sorry, Z. Yes, sorry. It's a pullback. So you can pull things back. We don't know yet this is a six functor formalism. In fact, you shouldn't have. It's like some smaller thing that you should isolate to where you have some possible six functor formalism, but there's a pullback thing like that. That's all I'm going to use. Okay. So the key thing I want to use is that the theorem. Okay, so this is a home for cohomology theories like Salmon K theory, like algebraic K theory, and so on. So what NLI was a proof is that the formation of algebraic K theory is stable under pullbacks. Z is the same thing as KGL. Okay. Okay, but this is NLI also. But what they really prove is the Slave theorem. It says that if I take like the motive of BGM, whatever that means, and I invert some elements, I get K theory. So this is the motivic Slave theorem. Okay. But it also proved something slightly better, and it answers. It makes precise that Selma K theory is the better is the better étale K theory. So they also prove the following. Okay, if I take this motive of BGM and I take this beta inverted, so this category motivic spectra, things do not have étale descent. They're not étale sheaves. They're only Nisnevich sheaves. But if I étale localize this, then I'm going to get a spectrum that represents Selma K theory. Okay, so concretely, what it says, okay, so this is like the real content of the whole theorem. If I take algebraic K theory, usual normal algebraic K theory, and I étale sheafify this bad boy.
Sure.
Okay, there's no reason why this has any good properties. There's no reason why this has the projective bundle formula. For example, that's the key point. Now, you étale sheafify, how do you compute étale K theorem P1? Right? And that's what they did. So LPBF is K sub. That's the real content of anomaly Watson. That if I further do projective bundleification, like impose that this thing takes P1 times X to 2 copies of X, then I get Selma K theory. And that's the magic.
So the first thing is what you'd call, before you project the bundle formula, that's what you call bad étale K.
Yes, there's the bad étale K theory. You just étale sheafify as a sheaf of spectra or like sheaf of spaces, whatever. Just blindly do it, right?
What is the value of that thing on P1?
I don't know. It's hard to compute. It's impossible to compute. Yes.
It's just a logical model that the reason to describe KU and also
The Snaith theorem. The Snaith theorem, yeah. Yes. So Snaith proved the following. If I take suspension infinity plus of CP infinity, right? And I invert the following line, 1 minus O minus 1, that's the correct element. And I invert this element, then I get KU. Yes. So this is what makes it stable on the pullback, because the pullback of CP infinity is stable wherever you pull back. So that's what they do. Okay. Yeah. So the content again of like this calculation is the fact that Tony and Ryomi could compute étale K theory of. They could compute basically étale K theory of some Grassmannians of like cellular varieties.
so C1.
Yes. Yes. Exactly. Yeah. Yes. All right. Okay. So this, I'm going to use this. So you notice that motivic, like étale K theory or Selma K theory is stable on the pullback. So I just have to define the filtration on MSZ and then pull it back and then recompute everything. So you can give a filtered refinement of the pullback square defining Selma K theory, but you don't do it by gluing. You just compute it afterwards. That's the strategy. That's the point. So the construction. Okay, I won't have time to explain this, but of course, feel free to ask me. So you can take the slice filtration. So the slice filtration is something which is A1 invariant. So this is kind of bad, but I do it over Z. So KGLZ. Okay. Now, so this is inside the world of A1 invariant motivic spectra, which is the old world of Voivodsky. Okay. And then I étale sheafify or étale localize. This is really étale PBF, but not in the A1 invariant world. I just do this thing in another Holera Iwasa's category, the Ahoy category. And then I pull back. Okay. So this is a motivic spectrum. There is a way to like take global sections, which used to be just a filtered spectrum, and I just do that. So that's the construction. It's just like, yeah, you do this very weird thing where you take this A1 invariant, Voivodsky size filtration, you forget it's A1 invariant, you étale PBF sheafify, and you pull back. So how on earth can you compute that? Well, the point is that the graded pieces of this, after p-completion, after rationalization, are left unextended from smooth Z schemes. And that's what gives you control over this thing. So yeah, you just really have to understand fully this object over smooth Z schemes. Yeah, so that's the construction. I think I'm done.